Hey everybody, this is going to be a random type problem review for your final exam. Basically, let's see, I gotta get the pen working here. So once again, I hope you attempt the problems prior to actually working them out. That's the important thing, and I'll kind of give you some insight. So looking at the very first problem here, the Delgado Soft Drink Club has determined that 35 members' favorite drink was Coke, 20 members' favorite drink was Pepsi, and 59 members' favorite drink was Swamp Pop. One member is selected at random, and we want to know the probability their favorite drink is Swamp Pop. Now, the fundamental definition of probability, let me get rid of this, okay? Like I said, unedited. Get what you get. All right, well, anyway, the basic definition of probability is the number of ways you can do something. Well, there are 59 ways we can pick someone who drinks Swamp Pop. That's divided by the number of ways we can pick anyone. That is a fundamental definition of probability, right? How many ways you can do it to how many ways you can do anything. Well, we have 35 plus 20 plus 59, a total of 114 members of the drinking club. So the fraction 59 over 114 is the probability someone is selected who favors Swamp Pop. Moving on to problem number 2, problem number 3, and problem number 4. Let me mention the relationship between the three problems. Each of these problems is about the percent of data in an interval. Okay? If you look at these problems, I gotta get away from the button that, which they wouldn't have this button here. Interval. Okay? That is, let's look at the first problem. We want the percentage of cupcakes that are between 4.5 and 6.5. Let's look at number 3. We want the proportion of TV sets that are less than 20.54. Percentage, probability, proportion. They all really in a way mean the same thing, right? Problem number 4. Wait. Let's see. Where am I? Oh, problem 2 and 3. I'm sorry. 2 and 3. I was thinking 4 was the same problem. No. All right. So, whenever we have a problem that is about the percentage of data in an interval, we have 3 things to consider. 1, Chebyshev's formula, which is 1 minus 1 over k squared. The empirical rule, okay, that is 68, 95, and 99.7. 1, 2, 3 standard deviations, right? And finally, the normal, right? And that means the table, correct? So when we're asking questions about the percentage of data in an interval, if we say nothing about how it's distributed, we work with Chebyshev's formula. If we are told the distribution is bell-shaped, the empirical rule. If we're told the distribution is normal, we're going to get to the table, right? Subtract the mean divided by the standard deviation. That's how you get to the table. So you have to keep that in mind whenever the question is about the probability, the percentage, the proportion of data in an interval. You have 3 options here. Okay? So let's get working here. The mean weight of a cupcake at Cupcake World is 5.5 ounces. The standard deviation is 0.05. And we want the percentage of cupcakes that weigh between 4.5 and 6.5 ounces. So we are looking for the percentage of cupcakes that are in an interval. And that interval ranges from 4.5 to 6.5. We're not told anything about the distribution, so our only option here is to work with Chevyshev's. Chevyshev's requires the interval to be centered at the mean. Well, mean is 5.5. The distance from 5.5 to 6.5 is 1, and the distance from 5.5 back to 4.5 is 1. So it is centered at the mean. If we're going to work with Chevyshev's, let me erase this stuff over here now. If we're going to work with Chevyshev's, we need to know the number of standard deviations we are from the mean in terms of the endpoints, right? So if we look at our problem here, our standard deviation is 0.5. The distance is 1, but we need to know the number of standard deviations we are from the mean. So we divide distance by the standard deviation, and we are k standard deviations from the mean. Think about it. A half and another half gives you 1. So therefore, by Chevyshev's theorem, the percentage of data in this interval is 1 minus 1 over k squared, okay, which, show yourself, is going to be 0.75 or 75%. Okay? Got it? All right, so that's Chevyshev's. Now, the second part of number 2, we are assuming a bell-shaped distribution. Well, for a bell-shaped distribution, we have what we refer to as the empirical rule. And that says that if our data is within 1 standard deviation of the mean, okay, that percentage is going to be 68%. If we are within 2 standard deviations of the mean, it's going to be 95% of the data. If we want to be within 3 standard deviations of the mean, then we can conclude that 99.7% of the data is going to be in the interval. So 1 standard deviation, 68% of the data is in the interval. 2 standard deviations, 95% is in the interval. 3 standard deviations, 99.7%. So we're looking at the same problem above. We are centered at the mean. These 2 problems require that, and if not, you have to, quote, adjust if you can, but it is a requirement. Once again, we're 1 unit, but we need to know how many standard deviations we are. We've already done that calculation already. K was equal to 2. So if we assume a bell-shaped distribution, then the percentage of data in the interval is actually 95%. That is, the more information we know, the more accurate our conclusion can be. Without knowing anything, the only thing we can assume is that at least 75% of the data is in the interval. But if we go to a bell-shaped distribution, we can up that number, and now I know that 95% of the data is in that interval. Moving on to number 3. For problem number 3, we have a TV set whose average length is 21.19 centimeters with a standard deviation of 0.65. We are assuming TV lengths are normally distributed, and we want the proportion of TV sets that are less than 20.54. Okay? Well, what do we know? We are looking for the probability that X, our TV set, is going to be less than 120.54 centimeters. We're told this thing is normally distributed, so we need to get to the table. We get to the table by subtracting the mean and dividing by the standard deviation. You can show yourself this is the probability that Z is less than -1. Z is less than minus 1. So if we go to the table, I got a normal table here, y'all. So we look up minus 1. There we have 1587. 1587. So the probability that our TV set is less than 120.54 is 1587. So that is another way of saying it is about 16% of your TV sets are going to have their length is going to be less than 120.54 centimeters, all right? But notice these two problems. How are they related? We're looking for the percentage, the proportion, the probability of being in an interval. First one, we're not told anything about the distribution. Our only hope is Chevyshev's. For the second one, we're told it's bell-shaped. We hope to be able to use the empirical rule. And for the last one, the strongest statement we can make, it's normally distributed. We need to get to the table. We get to the table, and this is the way the table works. So whatever the table tells us, that's the percentage of data. That is TV sets that is less than 120.54. So 15.87%. Number 4. At Delgado, 45.7% of your students take online courses. A student is selected at random, and we want the probability they do not take any online courses. Notice that taking online courses and not taking online courses are opposites of one another. They are complements. And when you take the probability and add two complements up, it has to add up to 1. So to determine the probability they do not take any online courses, it's 1 minus the probability they do. And so when we do the math here, we get 0.54, or 54% of Delgado students do not take any online courses. Got it? Moving on, again, I am assuming you have worked these problems. All right, number 5, we want to compute the mean for a probability distribution. When we're given the outcomes along with their associated probabilities, as here, the way you calculate the mean is you multiply outcomes to their respective probabilities. So I am going to be multiplying these numbers to one another, and then I'm going to be adding these up. And that's how we calculate the mean when we're given the probability distribution. We're not given the data here. We don't add up the 5 pieces of data and divide by 5. No, we're told what the outcomes can be and what the respective probability of being that outcome is. So we multiply probabilities to their outcomes. First one, negative 0.1 plus 0.275 plus 0.7 plus 0 plus 0.875. When you add this together, you get 1.75, and that's the expected value or the mean associated with this probability distribution. The last thing I did with this particular review, I said a few things about histograms. Now, I will note, I might have said something backwards in class, I'm not sure. But basically we say a histogram is skewed to the right if most of the data is to the left. It's backwards, right? See, in this particular histogram, most of the data is towards the left. There's what is called a tail to the right. This is skewed to the right. Okay? In B, notice most of the data is towards the left. When data is shifted to the left, then we say it is skewed to the left. Okay, hold on, let me make sure. Most of the data here is to the right, correct? Notice most of the data is to the right. So we're saying this is skewed or left skewed. I had it right. I was right. Left skewed. Okay? It's kind of backwards the way. To me, I don't know, but that's the way they do it. Again, when the data is mostly towards the left, we say it's right skewed. When data is mostly towards the right, we say it is left skewed. If the data looks like it's very grouped in a center, we just say it's symmetric, it is centered, that sort of thing. Okay? And that is it for this particular one.